Okay, let's start. In the last class, we briefly looked at noise. So again, just to recap, the deal is the following. If you have a resistor, the noise generated by the resistor is modeled this way. We assume that the resistor is noiseless and the noise actually is generated by a hypothetical voltage source. The polarity doesn't matter. Or you can assume that the noise is generated by an hypothetical current source in parallel with the resistor. So the one-sided power spectral density of the voltage noise is 4 kT times R. For the current, it is 4 kT by R. Now similarly, for a MOSFET, we have the same situation. We have thermal noise. So once again, to model the noise in a MOSFET, we do the same thing. We assume that our MOSFET is noiseless, but the noise is generated by a hypothetical noise current source put in parallel to the MOSFET. And when the MOSFET is in saturation region, the power spectral density of this current is 4 kT gamma times Gm. Now we also saw, in addition to this thermal noise, in MOSFET there is also what is called as flicker noise, whose power spectral density inversely varies with frequency. But the deal is, thermal noise is something fundamental that comes from thermodynamics. Flicker noise is coming because of imperfections in the manufacturing process. So this is not really fundamental. And then we saw if we have any linear network that we make, or any network that we make using MOSFETs, resistors and stuff, and here if you go and connect the input, and let's say at the output you look at the output voltage, or let us say you are interested in the short circuit current. For example, I'll take a short circuit current. Ideally, you expect that the contribution of at the output, you expect only the input to appear, but now you know you'll have noise sources. So let us say I have multiple noise current sources in my network. Now we'll have contribution from all of these noise current sources also to the output. But one nice thing is, the input signal that we apply is a small signal, and so are the noise current sources. Their amplitudes are going to be very, very small. So although your network might be nonlinear, we can say that for small signals you can approximate as a linear network, which means you can nicely use superposition. So to find only the contribution of the noise, what can I do to the input? I can de-energize the input, so the input is shorted. Now I'll be able to compute only the noise, and this also we use superposition. We take one noise source at a time. Let us say I take the kth noise current source having a power spectral density Sik of f. I find the transfer function from that noise current source to the output. Say that transfer function is some hk of f. The output power spectral density is the input power spectral density times magnitude squared of the transfer function it sees, and then you do it for all the noise current sources and sum it up. So this gives the final power spectral density of the output current. I'll put it here. Again, please remember, we are able to directly write the power spectral density of some of the individual powers or individual power spectral densities, because the noise sources we are considering, they are uncorrelated. They have never seen each other in their lives before. So if they are uncorrelated, you can directly add the powers or power spectral densities. Okay. But then we saw the convenient way to model the noise in any linear network is this. Again, we follow the same pattern, mindset of Indian parents. We'll say that our network is noiseless, but the actual culprit is some hypothetical noise voltage source that we put at the input. So here there is no noise. We'll say that this is noiseless. Again, the polarity of this voltage source does not matter, because finally you are interested in the power. But then we noticed this works well if the source resistance is 0, but in practice we do not know what will be the source resistance with which the input voltage will be connected. So if you have a finite source resistance Rs, so let me show the source resistance here. Then we notice that this noise voltage, only a fraction of this noise voltage will appear across the input, because now we have a resistive division between RS and the input impedance. And in particular, if RS is very, very large and if RS is infinity, this model predicts that the noise voltage does not appear at the input at all. But that's not what happens. You still have noise generated in the network. So to properly model the noise, in addition to the voltage, you also need to have the current. So I'll call this IN in, and this is what we call as the input referred noise. And you can clearly see, if I consider two extreme cases, let us say one case where RS is 0. If RS is 0, which of the two elements contribute to the noise, voltage or the current? Voltage, because the voltage source is directly appearing across the network and exciting. Current source will flow through the voltage source. The current will flow through the voltage source. So if I have RS to be 0, I have the noise only due to the input referred noise voltage. Similarly, if I take another extreme case wherein I take RS to be infinity, which means this is open. Now which of the two will contribute to noise? Current, because voltage source is open. This is open circuited now. Okay. Okay. Yeah. So if RS is infinity, I'll write it here, or I'll write it here itself. I have the noise only due to the noise current. But the problem is, in practice, you do not know what might be the value of RS. So for any value of RS, if you want to capture the noise in the network properly, you need to have both. That's the final idea. Okay. Okay, good question. So let me redraw the same thing. So I have one voltage source, one current source, correct? And I have, let us say, this is the input impedance of the network, Zn. Now I am shorting this. Right? Now if you want to find the contribution, you use superposition. I have two independent sources, two sources. I want to find their contribution. I'll do superposition. For example, if I open the current, the entire voltage source appears across the input. No worries. Now if I want to find the contribution due to the noise current, what will I do? I'll short the voltage source. If I short the voltage source, what fraction of the current flows through the input impedance? 0. Correct? So that's why if RS is 0, you have noise only due to the voltage. Sense? Great. And towards the end, we also briefly saw how we might go about calculating the voltage and noise currents. The idea is simple. If I want to find the input referred noise voltage, it should make sense that we look at a situation where the noise comes only due to the voltage. And in what situation it happens that way? For what situation? When RS is 0, you see noise is only due to voltage. So you consider this case. So here also you go and short the RS. And in this network, you go and find what is the noise current this way. And the idea is, our model should exactly capture this noise. So equate the noise current power spectral density in the actual network and the model here. And in this network, you can find the power spectral density this way. In this network, the only noise element is this. So the output power spectral density is the power spectral density at the input times the transfer function you have from the input to the output. You equate the two, you get the voltage power spectral density. Similarly, to find the input referred noise current, you consider RS to be infinity. So, and although I am looking at the short circuit output current, we can also do the dual. We can look at the open circuit voltage also. We can do either. The final result will still be the same. So we'll look at a few examples so that things become very clear. It's not that difficult. But before that, 2 points I would like to make. So tell me this, the voltage and the current here, both of them are capturing the noise of the same network, right? If that is the case, do you think the VNN and INN, they are correlated or uncorrelated? They should be correlated. They are modeling the noise of the same network. So it should make sense that they should be correlated. So that is one important point. you can't treat them as independent noise sources, they are highly correlated. Second is this, we already know that if Rs is 0, the noise comes only due to the input referred noise voltage. Now let us say I consider a situation wherein the input impedance of the network is infinity. If my input impedance is infinity, then can you make any comment? Do you think we'll still need both voltage and the noise, or one of them might be sufficient? Yeah, you can look at the same thing. So I have the same, we can look at this simplified model. So I have Rs here. We don't know what is the value of Rs, remember. Now all I know is this is open, input impedance is open. Now which will be contributing to the noise? Voltage. Because now if you look at the voltage here, it's going to get divided between Rs and an open circuit. Entire voltage will appear across the open circuit. Look at the current. The current obviously will not flow here because this is open circuit. So here the current will not contribute to the noise. Only the voltage will be the contributing factor. This is clear? So I'll mark that also. If Zn is infinity, you have noise only due to the input referred noise voltage, and you can have the other case. If Zn is 0, the same thing, noise will be only due to current. Good. So now let's look at few examples so that things become apparent. So as usual, I'll start with simple cases. We'll do the calculation completely, and then for our op amps we'll use that understanding to write the result directly. So we'll start with the simplest example, common source. So let me take this. I'll draw the incremental equivalent, and for simplicity I'll ignore R0 for all transistors. So for common source, this is the output and this is the input. So which means at the input, let us say I have an input applied with the source resistance Rs. Now I am interested to find the input referred noise voltage and the noise current. What will I do for the input for that? I'll make the input to be 0, so voltage source, so it becomes shorted. So let me take this. So first of all, tell me what is the input impedance of the network? Infinite. So do I need to compute both voltage and the current, or one is sufficient? Only voltage. But let's actually religiously compute both the voltage and the current. If our understanding is correct, if I compute the current, what should it come out as? 0. Let's verify if that is the case, then we can move on. Okay. So for the first example, I'll compute both voltage and the current. Let's say I first want to compute voltage. What will I do for the source resistance Rs? I'll make it 0. So which means I'll short this thing. So how many noise elements are there in this circuit? 2, the resistor and the MOSFET. So let's say I model both their noises using a parallel current source. Let me call it INRD. Let me call this INM. Again, please remember the sign of the current source does not matter, but if you assume something, you stick to it throughout the calculation. That's all. So now my goal is the following. I want to make sure that I am able to model this noise in the circuit using input referred quantities. So which means I will assume that these are noiseless, but the noise is coming due to something at the input. So I'll have an input referred noise voltage and the noise current at the input. And here is where you typically connect your input with source resistance Rs. This is the actual model. Now here Vin is 0, Rs is 0, so this is shorted. Make sense? So again, now I can either look at the open circuit output voltage but in many cases it's easy to find the short circuit current, so I'll consider short circuit current. Now it's all plain old small signal analysis. Now I have two currents. Tell me what might be the final output current. In terms of the individual currents, what is I out? Sum of the two currents, it's all plain small signal now, right? So it's IN, let us say RD plus INM. So I'm interested in the power spectral density. If I write the power spectral density, what will that be? Yeah, sum of the power spectral densities of the two currents. Again, I'm able to do this because I'm assuming that the two noise currents are uncorrelated. That's in fact the case. Okay, because it is uncorrelated, I am able to write the power spectral density as sum of the individual power spectral densities. What is the power spectral density of resistor noise current? 4 kT by RD. Similarly, for a MOSFET, please recollect it is 4 kT gamma times G. So this is the noise in my actual circuit. Now I have to make sure the same thing happens in my model. So I'll short circuit the thing. So in this model, I know obviously only the voltage is going to contribute. This is not going to be there. So at the output, I'll have noise only due to the voltage source VNN. So the output power spectral density here will be the input power spectral density times what? Gm square. I just have to find the transfer function from this voltage to the short circuit current. That is essentially the short circuit transconductance, which you already know it is Gm. Is this okay? Oh, I mean, remember power spectral density, it is the output power spectral density is the input power spectral density times magnitude squared of the transfer function, right? It's all power, so things are squared. So if my model is correct, these two quantities have to be equal. So I'll directly equate the two. Right. From this we can directly find SVNN. So I'll just write it for simplicity, just 4 kT by Gm square RD plus 4 kT gamma by G. This is what I get. Essentially divided this whole thing by Gm square. So idea is pretty simple. You just find the noise current in your actual circuit, find the transfer function from the appropriate voltage or the current to the output quantity, and divide the power spectral density you computed here by the magnitude squared of the transfer function. So only thing you have to do is, I mean, this is pretty simple. All you need to do is understand small signals. You're essentially finding the transfer functions from each, like different currents, different voltages to the output. This is all your plain old small signal, whatever you did in your first 2-3 mini quizzes. That's it. The extra piece of information you have to remember is, power spectral density of resistor is this, MOSFET is this. So this is the voltage. Let's also compute the current. And if our understanding is correct, the current should be what? Should come out as 0. Let's verify it. I'm interested to find, let us say, the input referred noise current. What will I use for RS? I'll make it infinity. So which means this is open, this is also open. So here the contribution will be only due to the current. The first step is the same. You might find some noise current. Okay, let's not go into that. Let's look at the transfer function here. So I'll erase this. Now I'm interested to find the transfer function from the noise current IN to I out. What is that? If I apply a current source at the gate and I'm interested to find the short circuit current here, what will be the ratio of this to this? 0. Why? Sorry? So will it be 0 or something else? I mean, he's saying the current cannot flow through the transistor. I mean, if you are not comfortable with limiting cases, the simplest thing is to assume that you have some R here. My Rn is ideally infinity. Let's start with Rn and we'll tend Rn to infinity. If the input resistance is Rn, what will be the gate voltage? I times Rn. if Rin tends to infinity, what will happen to gate voltage? So this will go to infinity. What will be the short circuit current then? Gate voltage is infinity. What will be the drain current? Right? So what is the transfer function from the IN in to IOut? Infinity, right? So which means if I find this path spectral density divided by infinity, I'll get. Okay. So that's why here you can write IN in as 0. So from now on, any example we see where the input impedance is infinity, we can straight away write that the input referred noise current is 0. I mean, please remember, the input impedance is not exactly infinity, right? You have a capacitance here, right? At high frequencies, you have a finite input impedance, but for simplicities, we are ignoring it. Okay. If you include the gate capacitance also, then you will actually have a non-zero noise current. So at high frequencies, this is very important to be captured. Okay, so this is simple. Now let's look at second example. But before that, I'm hoping that the calculation is fine. So let's do a couple of them more, so then you'll get a feel for it. We did common source. Now let's maybe look at common gate. So have common gate means I have, let us say gate is incrementally short. I apply the input here. I take the output from the drain. So which means I'll have RS and V in here. So as usual, I am computing the noise, so I'll make sure V in is 0. So this is short. So now what is the input impedance of the network? Let's assume R naught to be infinity. What is the input impedance? 1 by Gm. So now I need to find both voltage and the current, right? So let's start with voltage. For finding the input referred noise voltage, what will I assume for the source resistance Rs? 0. So let me redraw the circuit for Rs equal to 0. So this is essentially shorted. And as usual, I have two elements that generate noise, which is the MOSFET and the resistor. I'll model their noise as current sources like this, say INRD. And let us say and I look at short circuit current. And my goal is to make sure I'm able to capture the noise in the network using this model. So in my actual model, the elements are assumed to be noiseless and the noise is assumed to be coming from an input referred noise voltage and current. Let's see if we can make space. Rs is 0, so this is short, and I'm finding the short circuit current. So let me also. This is fine. Now tell me what is the I out here in terms of the two noise currents. What is I out? Again the same thing, sum of the two currents. So I can directly write the path spectral density. Path spectral density of the resistor noise current is 4 kT by RD. Path spectral density of the MOSFET's noise current is 4 kT gamma times Gm. Same thing we computed for the common source will be valid here also. Now all I need to do is in this network I should find the transfer function from the voltage source to the output. Again, the current source will not be pumping in any energy, right, when Rs is 0. Now I have to find the transfer function from the voltage Vn in to the current I out. What is that? this voltage is, let us say, VNN. What will be the current? Gm times VNN. So the transfer function, let us say, magnitude of the transfer function is Gm. To find the input referred noise voltage per spectral density, I will take this quantity divided by Gm square. That's all. I will not simplify it. Just the procedure is what is important. Okay. So the job is only half done because we have only computed the input referred noise voltage. We also need to do noise current. So what will I do to find the noise current? I will make Rs to be what value? Infinity. So let me erase all this. So if I make Rs to be infinity, at the input side it's open circuit. Okay. So here it is open. Rs is infinity. So same I will do here also. I will open this. Okay. Now tell me what is short circuit IOUT. First tell me how much of this resistor's noise current will flow through the output. The entire current of the resistor's noise will flow through the output. That much is clear. So this fellow is done. Let's ignore it. Now how much of this noise current will flow through the output? 0. 0. Why? Okay, it's open circuit below. So if this current is, say, some I1, what can you say about this current? I1, because no current flows into the open circuit. So which means this current and this current both are equal. Then what is the current flowing out? 0, right? I mean the current 2I1. Right? Yeah, I mean this current is essentially some difference between the current flowing this way and the current flowing down, right? Both the currents are equal, so IOUT is 0. So okay, because this current will essentially circulate within itself. Okay. Oh, good question. Why is it not circulating in the previous case? Why not? Here, this is, I mean, remember that for current to flow in your circuit, there should be a closed path. Right here, this is open circuited, whereas here you have a closed network because these two are grounded. I mean, it's your, basic circuits courses, so please go and think, right? I mean, might not be very apparent, but think about it, it should be. So this is the final path spectral density, this is the final current. So what is IOUT of F? 4 kT by RB. So this is one part. Then I just have to find the transfer function from the input referred noise current to my short circuit output. Again, I know the voltage source is open, it's not relevant. So what will be the transfer function from the current IN into IOUT? 1. Whatever current you are pumping in is going to flow here. Again, I'm ignored R naught, so no need to worry about anything. So the transfer function is 1. So my input referred noise current will have the same path spectral density. Okay. So again, I mean, this is pretty simple noise calculation. As long as you are comfortable with small signal calculations, finding transfer functions from each different voltages to different outputs, this is actually a cakewalk. That's why I made sure noise is all introduced towards the end, because the only thing you have to remember for noise is what is the path spectral density for resistor, what is the path spectral density for MOSFET. Everything else in any circuit design, the main important point is understanding small signal behavior. If I have a small signal voltage or small signal current, how the circuit functions. That's the important thing. The rest is all minor things that you can pick up anytime. Okay, so then let's look at third example. So I'll consider this case. So it is can think of it as a common source with a resistor at the source side. So I'll draw the small signal picture. So I'll call this RD, I'll call it RX, and here is where I apply the input and I tap the output from the drain. So which means if I were to draw it properly, I apply the input at the gate like this with a source resistance Rs, right? So as usual, for noise calculation, input is shorted, so V in is 0, so the this node is shorted. Okay? So let's repeat the same thing. So now what is the input impedance of the network? Infinity. So do we have to compute both voltage and current? Only voltage is sufficient, right? So I'll find only the noise voltage, because I'll directly write INN is 0 as Zn is infinity. Straight away you can write it. And for finding the input referred noise voltage, what do I do for the source resistance Rs? 0. Fine. So let's repeat the calculations for this. Rs is 0, so this fellow is shorted, and I'll do the same here. Here I have my input referred noise voltage and the current, and this is short. Again, I know the current is not going to contribute, so I'll just cross it out. And as usual, I look at the short circuit output current. Again, you don't have to look at the current always. You can even calculate the voltage here and do the calculations. You will get the same result. But many times currents is easy because you are shorting things, so things are simplified. And again, as usual, I'll ignore R0. Okay. Now let's look at my actual circuit. How many elements contribute to noise here? 3 of them. Let me model all their noise currents. So let us say this is INRD, this is IN of RX, this is IN of M. So again, let's compute contributions one by one. How much of this noise current INRD flows to the output? Entire current flows to the output. So using superposition, I will compute one by one. So this is INRD. So this is done. So I'll take it off. Now let's look at this fellow. I have this current INRX that is getting pushed into this node. Again, I am using superposition, so I will not ignore the MOSFET's current for now. Okay, let's remove it to avoid clutter. This current is getting pushed here. So how much of it will flow through the output? Will the entire current flow through the output, or something will happen? Current division between what and what impedances? What is the impedance looking up? 1 by Gm. So how much of the current will flow through the output? Yeah, Rx by Rx plus 1 by Gm. Okay, current division. I am interested to find the current flowing into the impedance 1 by Gm. So I will look at the other resistance Rx by Rx plus 1 by Gm. Okay, so this is done. So I will remove this. Now I just have to find the MOSFET's noise current. And I mean, computing the effect of this current is not very trivial, because in the previous two cases, one of the terminals of the current source was grounded, but here you have a floating current source. I mean, it is easy to calculate, but not trivial. So you can do it in multiple ways. I always like to do the following trick. So let us say I have two nodes A and B, and I have a current source connected between the two nodes I. This is the scenario I have, right? This can be node A, this can be node B. Now I can do the following. I can consider it as though I have two identical current sources connected like this. Nothing changes. Now what might be the voltage at this node here? Undefined. At this point, that much should be clear. This is undefined, which means this can be any potential in the world. If this can be any potential, what can I assume this to be so that my calculation is easier here? Huh? Why 0? Someone told 0. I don't know who told. Who told? You told. Someone told 0, is it? Yeah, I mean, remember that, the reason that the calculation here is tricky is because it is connected between two nodes. In my earlier two current sources, it was trivial because one of the terminals was grounded, right? So here if I assume that this is grounded, things are easy, right? So this can be treated this way. I'll assume as though I have one current source connected from node A to ground, other current source from ground. Node A is not connected to ground. No, that is okay. Remember that it is connected to ground, but you are interested in finding the current here, right? So that way I am not considering it as ground. Okay. So now you see in the actual circuit I was pulling out a current of I from the node A. That is accomplished by this current source. With respect to the node B, I should be pushing in a current I. That is accomplished by this current source. The only thing to be very cautious is make sure that the direction of the current is maintained. If you mess that up, calculation is gone. I prefer to do it because as you will see, things become very easy. So I'll remove this for this case, or maybe I'll move to next page. It can be anything. If it can be anything, it can be ground, right? What is wrong? No, what I'm saying is this is only for calculation. This is not actually happening in the network, right? Only for your calculation you can assume it to be ground. But in actual circuit, if you have two current sources with MOSFET, then you should not do this. Okay? This is just for ease of calculation I am doing it. Okay? So I'll ignore this. So now I have this floating current source. What I'll do is this, as of now the current direction is down. I'll assume that I have two current sources now. So same current flows. Now it should be very clear, right? Whatever happened for your resistor's noise current will happen with this current source. We can use superposition. Let's say I find only the contribution of the first current source. I'll not ignore this. I'll ignore this. So whatever happened for this will happen for this. So how much of this noise current will flow through the output? Can you tell me the correct polarity? Minus INM. Straight away it's done. So now I'll look at the other current. Now remember, this current is behaving the same way as a noise current for your resistor Rx. Whatever you did for the noise current of Rx, same thing you will do for this current source. So that will be plus INM times the same, division. That's all. This way you don't have to do extra calculation, it's straight away done. I'm not saying you should always compute it this way. You can still consider it to be a floating current source, apply KCL and find the short circuit current. Completely fine. I'm just giving an alternate approach which I find it easy. If you find it easy, use it, otherwise you are okay. Finally, it's all small signal. I'm interested to see how much of the floating current source flows through the short circuit output. That's all. You do it any way you want. So this is done. So then let's quickly wrap up the calculation. You can assume to be anything you want. but the moment you assume, you stick to the polarity. That's all. Like I told, the noise, this is noise current, you are only interested in the power. The sign doesn't matter. But moment you assume something, you stick to it. That's all. So let's quickly wrap up the calculation. So I'll simplify this. If I simplify this, I'll directly write the path spectral density. Maybe I'll take it to next page and write. So path spectral density will be 4 kT by Rd plus, I think this should be 4 kT by Rx times Gm Rx by 1 plus Gm Rx whole square, plus this should be 4 kT gamma Gm by 1 plus Gm Rx whole square. This is my S iota of F. Okay, I've just simplified and written it. Don't worry about this, you can do it. Now I've just found the noise in the actual circuit. To find the input referred noise voltage, what should I find next? I'll find the transfer function from this voltage Vn to Iout. Can you tell me what will be the transfer function? I apply some voltage at the gate Vn. What will be the drain current? Gm? Yeah, how do you say that? Correct. How much will be Vx? GmRx by 1 plus GmRx. Source follower, I ignored R0 of the transistor. So what will be the current? This voltage by Rx. So the transfer function is Gm by 1 plus GmRx. This is the transfer function. So you take the path spectral density of this, divided by the magnitude squared of it, you get the input referred noise voltage path spectral density. So if let's try to do that. So I will divide this whole thing by Gm by 1 plus GmRx the whole square. If I do that, I mean the first term will be something 4 kT by Rd into something. Second term you can simplify it as 4 kT times Rx. I am not showing it, you can simplify it. Last term will be 4 kT gamma by G. Now here is where I would like to make a couple of points. Now just look at the last term here. So this is where I would like to make a point. So let's understand why the last term makes sense first. Now if I take a MOSFET like this, I know that the noise in my MOSFET, I can model it using a current source. What is the path spectral density of the current source? 4 kT gamma times Gm. Now let us say, what is the input impedance of this structure? Infinity. If I ignore the gate capacitance, it's infinity. If I were to model the noise of this MOSFET, now at the input side, what do I need to have? If I want to model the noise as an input referred quantity, what do I need to include here? Only a voltage source. And what will be the path spectral density of that voltage source? Yeah, it is the current by the gain. Gain is the gain from the input voltage to the output current. What is that gain? So here what should put here? Is this clear? I mean it's pretty, I'm not doing anything complicated. I know what is the output quantity. Output quantity has a path spectral density of 4 kT gamma Gm. I am trying to refer it back to the input. I am dividing by the gain square. The gain here is the gain from the input voltage to the output current. So this simplifies to, so which means if you have any time you have a MOSFET and if you ignore the gate capacitance, that means you can say that the input impedance is infinity. Then you can either model the MOSFET's noise as a parallel current source with a path spectral density 4 kT gamma by Gm, or you can equivalently model it using an input referred voltage source. Sorry, this is 4 kT gamma times Gm or here you can model it with the voltage source with the path spectral density 4 kT gamma by G. Yeah, I actually took a simpler case and showed it, but I'll give an assignment problem. That way you can convince yourself that even if this is not grounded, even you connect something here and there, you can still do this. But the condition is, we assume that the input impedance is infinity, which means I am ignoring the gate capacitance. So which means now if I look at the circuit I have, so I know that anytime I have a MOSFET, its noise can be modeled as a voltage source at the input. So which means the contribution of this MOSFET to the overall input referred noise voltage is simply the noise voltage of that MOSFET. I mean, because what I am saying is, instead of modeling the noise with a current source, I can as well put a voltage source like this. Now this is directly going to be contributing to your input referred noise voltage. So that is why the final expression also, you got this directly. And even if I look at the first example we saw, we have it here. Yeah, even in the first example, the input was connected to this MOSFET. So the contribution of this MOSFET to the overall input referred noise voltage will be 4 kT gamma by G. So anytime now you see that the input is given to the gate of a MOSFET, you can straight away say the contribution of that MOSFET to the overall input referred noise is directly 4 kT gamma by G. That you can straight away write it. Okay. So just look at one last case, and that will be your dear friend Cascode. I'm sure you use Cascode back and forth to increase the gain in your design project. So let's see what happens. So I'll just consider an NMOS Cascode like this, incrementally short, and here is where I apply the input, here is where I take the output. First let's even ignore R0. Now let's try to write things directly. I have two MOSFETs, M1, M2. First of all, do I need both voltage and current here, or only voltage is sufficient? Input impedance is infinity, so I can straight away write the current is 0, right? Now tell me, I have two MOSFETs, M1, M2. Input is connected to the gate of the MOSFET M1. What can you say about the contribution of M1 to the overall input referred noise voltage? You can straight away write it as 4 kT gamma by Gm of transistor M1. So contribution of M1 to the overall input referred noise is done. Now we just have to look at M2, that is a Cascode device, so that alone we'll do it. So again, to model the noise of M2, you can either use a voltage source like this at the gate, or you can put a current source at the drain to source. For now I'll use current source, but you can work out using a voltage source also, same thing you should get. So I'm trying to find the short circuit current. So let's say this is IN2. So as usual I have a floating current source. I'll try to replace it as two current sources. So what I'll do is this, I'll assume I have one current source this way, other current source this way. Let's say IN2, IN2. Fine. Instead of having one current source flowing this way, I split as two series current sources. Now you can straight away tell me how much of this IN2 will flow through the output. I ignored R0 of all transistors. How much of IN2 will flow through the output? I mean, this current can either flow down. I mean, remember I'm trying to only find the contribution due to this current source. First let me ignore this. So what is the current flowing this way? I have minus IN2, that should either get divided up or down. The R0 is all infinity. So how much of this current will flow through the output? 0 or fully? Fully, right? I mean, looking down it's infinity. So the entire current will flow up. So I out is what? That is due to the bottom current. Now let's look at the top current. So this I'll ignore now. How much of the top current will flow through the output? Plus IN2. The entire current will prefer flowing through the short circuit. So what is the total current now? So this is an important property you should remember for Cascode. Right? So Cascode is your very good friend who makes sure that, who improves only the nice things in you, make sure that the output resistance of your structure is improved, but make sure it doesn't spoil you in any other sense. That way it is not adding any noise. This is an important property of Cascode, that Cascode will not add any excess noise in your circuit. And again, this is exactly 0 because I ignored R0. Now we can include R0 and repeat the calculation. I'll give it as an exercise. You will find that I out will be IN2 into something, I think 1 plus GM2 R1. Okay, call it M1 M2. Just the voltage, current division you can work out and. But the idea is, as long as GMR is sufficiently larger, this noise current source will be, this noise current will be much smaller. So this is something to have in mind, that the Cascode device in general does not add a lot of noise. Again, this is ignoring all the gate capacitance and stuff, right? Cool. So hopefully you got a feel for how noise calculation is done. So I'll give out more examples in your this week's assignment. So please work out. Again, the fundamental understanding you should have is the small signal behavior. If you are very comfortable with finding how much of this current flows to the output, how much of this voltage appears here and there, this is actually pretty trivial. We'll stop here.